How are you all doing this morning?
Good.
So today we are going to be having our review session for our upcoming exam. So what would you guys like to talk about for today?
Do you think we could go back through Thevenin and Norton since it's been a pretty long time since we've talked about that?
Absolutely. So do you want to just kind of go over it in general, or would you like to work some problems specifically?
Can we maybe work a couple problems with Thevenin and Norton each, or
Do you want to work some from one of the old exams, or do you want me to pull some from a book or something?
it really doesn't matter. I just wanted to go over it one more time.
All right. Do you want the problem to have a dependent sourcing or not?
It can have a dependent source.
All right. So I've got a book in front of me. I'm just trying to find one that seems appropriate. Okay. So let's say that we have the following circuit. All right. So our goal here will be to determine the Thevenin voltage VTH, the Norton current I Norton, and the Thevenin resistance RTH. All right. So to find the Thevenin voltage, we take our original circuit, and we actually don't really have to do anything at all to it, except recognize that the Thevenin voltage will be the voltage drop across the open circuit set of terminals A and B, where I am choosing to have the positive polarity terminal be at terminal A and the negative polarity terminal of my Thevenin voltage be at terminal B. On your exams, hopefully that you have noticed from the practice exams that I usually specify positive polarity on top or positive polarity on the left or something like that. So you'll know exactly what voltage I'm talking about. So if we were to try to find this Thevenin voltage, the approach that I would use would probably be nodal analysis. So I would choose this bottom node here as my ground. And I'm just going to identify my nodes real quick. So that's one node. This is all one node. This is all one node. And this is all one node. So the reason why I chose the bottom node labeled in orange to be my ground is because I know that VTH will be, by definition, the nodal voltage at terminal A. So let's call this guy here VA so that it matches, minus the nodal voltage at B. And since node B is at 0 volts, that means that VTH is just going to be exactly equal to VA, whatever I find that to be. So I'm going to go ahead and call this guy here C, and this guy here D. So by inspection, I can see that VD is going to be 15 volts. Everybody okay with that?
Yeah, I thought whenever you were doing like Thevenin and Norton, is that only when you're doing the resistance, you have to like analyze it through like a dead network?
Right, that's only when you're looking for the resistance directly do you look at it with a dead network. We'll do that when we're looking at the resistance, and I'll go over the test source method, but I'll also talk about how to do it, how to find the Thevenin resistance another way as well. But when we're finding the Thevenin voltage and the Norton current, we need to be looking at the live network.
Okay.
All right.
Can you explain how VD is 15 volts again?
Sure. So VD is a nodal voltage. So the positive, so we would have the nodal voltage associated, let me write it in a slightly different way. 15 volts is equal to the nodal voltage associated with the positive polarity terminal, which is VD, minus the nodal voltage associated with the negative polarity terminal, which is 0 volts. So that means that 15 volts is equal to VD. So 15 volts is VD for the exact same reason that VTH, our Thevenin voltage, is VA. The positive polarity terminal of the 15 volt source is attached to node D. The negative polarity terminal of the 15 volt source is attached to ground.
Thank you.
Yep. Since our supernode there really contains the ground, we don't have to write a KCl equation for node D, so we will just have a KCl equation for nodes C and node A. So let's do KCl at C first. So to be clear here, I am adding this current, this current, this current, and this current together and setting them all equal to 0, or adding them together and setting it equal to 0. So that's going to look like VC minus VD over 3 ohms. That's the current directed to the left, plus VC over 6 ohms. That's the current directed to the down, minus 5/4 IX. That's the current directed to the right, plus VC minus VA over 4 ohms. That is the current directed up through the 4 ohm resistor. So anybody have any problem with my KCL equation at node C?
No.
All right, now we will do KCL at node A. So we will have this current plus this current is equal to 0 because we know that no current will flow to the right through the open circuit. So that's just going to be 5/4 IX plus VA minus VC over 4 ohms is equal to 0. And now we have to write our other equation where we express IX in terms of our nodal voltages. So IX, as it's shown in the circuit diagram, is the current that's flowing through a short circuit. But another way to think about it is before it's flowing from node D to node C through that 3 ohm resistor. So I could write an equation for IX that is simply VD minus VC over 3 ohms. Or 15 volts minus VC over 3 ohms. So I'm going to sub in 15 volts right here as well. And so this is 1, 2, 3 equations with 3 unknowns. So I'm going to solve these guys real quick. I'm going to get a number for VA, a number for VC. We know that VD is 15 volts. And while I'm at it, I'm also going to figure out IX. So,
Dr. Hartman,
yes.
why wouldn't IX just be 15 volts over 3 ohms?
Because node C isn't at ground.
Oh, okay. Thank you.
Yep. So, let's see. So this is going to be X, this is going to be Y, and this is going to be Z when I put them into my calculator. So I'm just making sure I'm not going to make some sort of dumb mistake here.
Dr. Hartman,
Yes.
can you explain how you got IX to be equal to VD minus VC over 3 ohms?
Sure. So do you understand where I said that IX is the current flowing through the 3 ohm resistor? Did that make sense to you?
Yes.
Okay. So when we're doing nodal analysis, we express currents as where the current is originating from, which is node D, to where the current is going, which is node C, and divide by that resistance value. So IX is VD minus VC over 3 ohms for the exact same reason that this current right here is VC minus VA over 4 ohms. It's just the voltage drop over the resistor divided by the resistor value.
Got it. Thank you.
Yep, and just to be clear, this guy right here is VA minus VC over 4 ohms because we consider it to be originating from node A and ending at node C. All right, so let's get back to that system of equations and start solving for stuff. All right, so in my first equation, my coefficient for VA is -1/4. My coefficient for VC is +1/3 plus 1/6 plus 1/4. And if I'm saying anything out loud that seems wrong, please stop me and I'll try to correct stuff. My coefficient for Ix is -5/4. And then my constant term will be +15/3. In my second equation, my coefficient for VA is +1/4. My coefficient for VC is -1/4. And my coefficient for Ix is +5/4. And my constant term is 0. In my third equation, I'm going to move that VC over 3 ohms to the left so that I will have 0 VA, 1/3 VC, 1 Ix, and that will be equal to 15/3. When I solve that equations, I get VA is equal to 5/3 of a volt. VC is equal to 10 volts. And Ix is equal to 5/3 of an amp. So from this, since TH is equal to VA, our Thevenin voltage is simply 5/3 of a volt. Any questions about the application of nodal analysis that we did there? All right, so let me copy this original guy up here again. When we are finding our Norton current, we take our original circuit, and we short circuit these terminals, and the Norton current is the current flowing through the short. So I'm going to approach finding my Norton current using mesh analysis, right? So when I tried to find a voltage, I used nodal analysis. When I'm trying to find a current, typically speaking, I'm going to use mesh analysis. So I'm going to have 3 meshes. Let's call this mesh I1, this mesh up here, I2, and this mesh down here, I3. Because there is a current source on the interior of the circuit, I'm going to have a current relationship. So I can see that 5/4 times Ix amount of current being supplied by that dependent source is going to be equal to I2 minus I3. Everybody okay with that? Mr. Menendez, how can I help you?
Can you hear me?
I can now.
Oh, you weren't hearing me before? Oh, I'm
Sir.
sorry. I'm sorry. I didn't mean to do that. I don't even know how I did that.
Oh, okay, no problem at all. Yeah, sorry. It just said that you had raised your hand and then it was quiet. I wasn't sure if you were typing something out or whatever. All right, not a worry at all. So now I'm going to go ahead and write my KCL equation for my super node, or excuse me, my super mesh. So I'm going to show you the path that I'm taking. I'm going to start down here at the 6 ohm resistor, go through the 4 ohm resistor, and then come back around like this. So my KVL at super mesh 2, 3 equation I'm going to have 6 ohms times I3 minus I1 plus 4 ohms. Actually, I3 minus I1, that's correct. Then 4 ohms times I2, and that's it. Any questions about my super mesh KVL equation?
So when writing the super mesh equation, you always want to go on the outside of the current source, in this case, the 5/4 Ix. That's where you write the current relationship separate, right?
Exactly right. So because I have 2 meshes involved in this super mesh, I need to get 2 equations out of it. One of them will be the current relationship and the other one will be the KVL relationship.
Thank you.
Now I'll write my equation for mesh 1. Let me. And so when I start at the bottom left-hand corner, I see the negative polarity terminal of the 15-volt source. Then I will have plus 3 ohms times I1 plus 6 ohms times I1 minus I3. Set this equal to 0. I now have 1, 2, 3 equations. Technically, I have another equation that I need to write, so I'll go ahead and do that real quick. My other equation, where I express Ix in terms of my mesh current. So what's that going to be?
Ix is equal to I1.
That's exactly right. So Ix is equal to I1. So I can substitute that guy into here. And now I have my 3 equations, 3 unknowns that I can easily solve. So let's solve for I1, I2, and I3, where I1 will be X in my calculator, I2 will be Y, and I3 will be Z. So I will say aloud what my coefficients are and all that kind of good stuff again here. So what I'm going to do is I'm going to move everything to the left-hand side of the equal sign for my first equation. So that means, that I'm going to have 5/4 as my coefficient for I1, -1 as my coefficient for I2, +1 for my coefficient for I3, and my constant term will be 0. For my second equation, my coefficient for I1 is -6. My coefficient for I2 is +4, and my coefficient for I3 is +6. My constant term is 0. In my third equation, my coefficient for I1 is going to be 3 + 6. My coefficient for I2 will be 0, and my coefficient for I3 will be -6, and my constant term will be 15. When I solve this system of equations, I get I1 to be 25/14 amps, I2 to be 135/56 amps, and I3 to be 5/28 amps. So how do I relate my Norton current to my mesh currents?
It's equal to I3.
Exactly equal to I3. Perfect. So that would be 5/28 amps. So I figured out my Thevenin voltage. I figured out my Norton current. My Thevenin resistance, I can do it in a couple of different ways. So I'll give you one way right now. My Thevenin resistance will be, by definition, my Thevenin voltage divided by my Norton current. So my Thevenin voltage is 5/3. My Norton current is 5/28. 5/28 of an amp. And so I think that's going to give me 28/3 ohms, but I'll double check here. 28/3 of an ohm. So that is one way to solve for the Thevenin resistance. And that's probably my preferred way to solve for Thevenin resistance whenever there are both dependent and independent sources in the system. But as practice, I'll scroll down here and we'll talk about finding RTH directly. So, as someone mentioned earlier in the class, whenever we're trying to find the Thevenin voltage, or excuse me, the Thevenin resistance directly, we need to be looking at a dead network. So what that means is that we will have to turn off our voltage source or replace it with a short circuit. All right. Now, because this network contains a dependent source, we can't simply just look in through these terminals and find the equivalent resistance. Instead, we will have to apply what's called the test source method. So in the test source method, I apply a test source to our circuit. I don't know yet whether it will be a voltage source or a current source. We'll talk about that in a second, but effectively, this is my voltage V test. This is my current I test, and the Thevenin resistance will simply be the ratio of V test divided by I test. So, would you guys prefer to work this with a test voltage source or a test current source?
Test voltage.
All right.
Which one are you more likely to put on the test is the one I want to work.
It doesn't matter. They give you the exact same answer.
Okay.
If they didn't, there'd be a problem. So let's work it once with a test voltage source, and then we'll work it again with a test current source and prove that we're going to get the same answer. How's that sound?
Awesome.
All right, so I'm going to arbitrarily choose a 1 volt source. So that means V test will be exactly equal to 1 volt. So now what I'm trying to find is that current I test. So I would tend to approach that using mesh analysis because I'm trying to find a current. So this is going to be my mesh current I1. This will be my mesh current I2. This will be my mesh current I3. And hopefully we can all see that I test, what I'm looking for is just negative I3. So I'm kind of giving you the reason that I am using mesh analysis there. So we have that interior current source again. So I'm going to have to say that 5/4 Ix will be equal to I2 minus I3. And we know that Ix is just I1. I'm going to have my KVL equation around my super mesh. So that's going to be pretty much identical to what we had before. So 6 ohms I3 minus I1 plus 4 ohms I2 is equal to 0. The only thing that's going to change here now is our KVL equation for mesh 1 because we turn that voltage source off. So it's going to look like 3 ohms times I1 plus 6 ohms times, oh, actually, I'm sorry, I made a mistake. So when I was doing KVL for my super mesh, and I'll draw it in purple again. I forgot to include the contribution to the test source. So instead of it being 6 ohms times I3 minus I1 plus 4 ohms times I2 is equal to 0, I now have to add 1 volt because I see the positive polarity terminal of my 1 volt source first as I go around that path. Okay, so I apologize for that mistake. So getting back to my KVL around mesh 1 equation, I have 3 ohms times I1 plus 6 ohms times I1 minus I3. Set that equal to 0, and I now have 3 equations with 3 unknowns. So I will solve for I1, I2, and I3 again. So, excuse me, my coefficient for I1 in my first equation is positive 5 over 4. My coefficient for I2 in my first equation is negative 1. My coefficient for I3 in my first equation is positive 1. And my constant term is 0. So that's the equation that didn't change at all. And excuse me, in my next equation, my coefficient for I1 is negative 6. My coefficient for I2 is positive 4. My coefficient for I3 is positive 6. And now my constant value will be negative 1 when I move that 1 volt to the right-hand side there. For my third equation, my coefficient for I1 is 3 plus 6. My coefficient for I2 is 0. My coefficient for I3 is negative 6. And now this is equal to 0 instead of 15 like in our last bit. So when I solve these guys, I get I1 is negative 1/14 of an amp. I2 is negative 11/56 of an amp, and I3 is negative 3/28 of an amp. And so if I put I test is equal to negative I3, so that's 1 volt over 3/28 of an amp, gives me 28/3 ohms, which, if I'm not mistaken, is the exact same result I got previously. So we have applied this test source method correctly. Let's do it again using a test voltage. Does anybody have any questions about that, I guess, before I jump into reworking it?
Just curious. I don't guess I heard you when you said it. So what is the reason for assuming 1 volt for the voltage source?
There is no reason to assume 1 volt specifically. We get to choose whatever test voltage we want. So I arbitrarily choose 1 volt, but you could choose 100 volts or 15 volts or whatever you want to there. Really doesn't matter. The result will be the exact same because of the scaling property of linearity that we talked about for exam 1. So the size of the voltage source does not matter at all. You can put whatever you want to there because it's going to be the ratio of the voltage divided by the current. And we know that if the voltage is larger, the current will be larger by the same amount or by the same scaling factor. Does that make sense?
Yeah, that makes sense. Thank you.
Mm-hmm. So we're going to do the same thing here. I'm going to turn off my voltage source. So I replace it with a short circuit. And again, I'm going to have some test voltage, V test, some current, I test, and this time I'm going to choose to use a 1 amp source. So because I'm trying to find this voltage, I'm going to use nodal analysis. So this is going to be my ground node, and I'm just going to quickly identify my nodes real quick here. That's 1. That's 2. That's 3. I'm going to call this node VA since it's the node associated with the A terminal of our circuit. This node will be VB, which is 0 because I've chosen to place my ground there. And so just for the sake of argument, this guy right here will be VC. I have no voltage sources whatsoever to worry about, so I can just simply apply Kirchhoff's current law at node C and Kirchhoff's current law at node A and solve that system to get V-test, where hopefully we can all see that V-test in this case is just going to be that voltage VA, and I-test will obviously be 1 amp because we chose it to be.
I have a question.
Yes.
So if we had a voltage source, say in node C or somewhere around there, would have to do a super mesh for whatever those two nodes were, say node C and node B, if we had a voltage source somewhere.
So if we had, it depends on if we had a dependent voltage source or an independent voltage source, because there is an independent voltage source in the circuit, but we turned it off. Because whenever we're trying to find the Thevenin resistance directly, we always look at a dead network, meaning all of our independent sources are turned off. So if there were a voltage source connected between node C and node B here, that would look like a short circuit in this particular circuit. Now, if there were a dependent voltage source, then we would have a super node condition that we would have to worry about.
Thank you.
So I'm going to do KCL at node C first. So that's going to be this current, this current, this current, and this current. So my current directed down through the 3 ohm resistor is just VC over 3 ohms. My current directed down through the 6 ohm resistor is simply VC over 6 ohms. My current directed to the right will be -5/4 IX. And my current directed up will be VC minus VA over 4 ohms. And I set all of that equal to 0. Now I'm going to do KCL at node A. I'm assuming nobody had any questions about that KCL equation at node C. If so, by all means, let me know and I'll talk you through it. All right, so I'm going to be adding this current, and this current together and setting them equal to 0. So the current directed to the left is simply 5/4 IX. The current directed up is VA minus VC over 4 ohms. And the current directed to the right is -1 amp. Set these guys equal to 0. And I'm going to have an other equation as well, where I define IX in terms of my nodal voltages. So IX is the current flowing through the 3 ohm resistor in this direction. It starts at ground, so that's going to be 0. It ends at node C, so that's 0 minus VC over 3 ohms, or just negative VC over 3 ohms. So I have 3 equations, 3 unknowns, so I'm going to solve for VA, VC, and IX. So in my first equation, My coefficient for VA is -1/4. My coefficient for VC is 1/3 plus 1/6 plus 1/4. My coefficient for IX is -5/4. And my constant term is 0. So let's see, -1/4, 1/3 plus 1/6 plus 1/4, -5/4. All right, that all checks out. For my second equation, my coefficient for VA is +1/4. My coefficient for VC is -1/4. My coefficient for IX is 5/4. And my constant term will be +1. In my last equation here, my coefficient for VA is 0. My coefficient for VC is +1/3. And my coefficient for IX is +1. My constant term is 0. When I solve this system, I get VA is equal to 28/3 of a volt. VC is equal to 2 volts. And IX is equal to -2/3 of an amp. Since we know that R Thevenin will be V test, which is just VA divided by I test, which is 1 amp, we get R Thevenin to be 28/3 of an ohm. So we've solved for that Thevenin resistance 3 different ways and gotten the exact same answer. So I feel very strongly that we have done it correctly in all 3 instances. So to the person who was asking the question originally, did you feel that that was an appropriate review of Thevenin and Norton circuit analysis? Would you like me to work another problem, or does that feel good?
No, that was really good. The only thing I was going to ask is, could you maybe explain one more time, like what you turn off, depending on if it's independent or dependent or not?
Okay, so when we are finding the Thevenin resistance directly, we turn off all independent sources, right? So if it's a circle, we turn it off. If it's a triangle, or it's not a triangle, a rectangle or a rhombus or a diamond or whatever the hell you want to call it, we leave that guy on. We can never turn off dependent sources. We turn off voltage sources by replacing them with short circuits. We turn off current sources by replacing them with open circuits. So when we're utilizing the test source method here, what we're doing is we are applying a forcing function of a known value to this system to see how it behaves. So what we're really doing is experimentally determining Ohm's law. When we talked about Ohm's law way back in the day on the 2nd or 3rd class meeting, we said that if we have any linear black box network that has a pair of terminals like so, the resistance of this network is simply the voltage drop across the network's terminals divided by the current flowing through into the network. That's exactly what we've done applying the test source method, but we can also do it if we apply a current source instead of a voltage source. It's literally just using Ohm's law to solve for that Thevenin resistance. All right, what would you guys care to talk about next?
You do a transient analysis problem.
Sure. let me grab a random different textbook. I have all my Circuits 1 textbooks on my desk right now because I'm working on a new set of notes. It's obviously going to be a first order circuit. That one is not a first order circuit. All right. So in the textbook that I'm looking at, this problem has a lightning bolt next to it, which supposedly means that it's difficult. Let's prove that wrong. Oh, actually, it's got a dependent source in there. That doesn't really make the analysis that much harder, but we haven't done anything like that, and I'm not going to put anything like that on the test. So I will just make that dependent source be not dependent anymore. All right. So I have a 4-volt source. A 2 kilo ohm resistor, a 150 microfarad capacitor, a 1 kilo ohm resistor. Let's make this guy a 4 kilo ohm resistor. And then I have my switch. And let's say that the switch is closing at t is equal to 0. I want us to determine the voltage drop across the capacitor, Vc of t, and the current flowing through this resistor, IR of t. So this is going to be a total response problem because the 4-volt capacitor, excuse me, the 4-volt resistor is always going to be influencing the behavior of the capacitor. Okay, so at t is equal to 0 minus, our circuit looks like this. We have our 4-volt source. Here is our 2 kilo ohm resistor. Since we're at DC steady state at t is equal to 0 minus, the capacitor is going to look like an open circuit. So this will be plus minus Vc at 0 minus. Here we have our 1 kilo ohm resistor. Here we have our 4 kilo ohm resistor. Over here, we have our 6-volt source. This is our current IR of 0 minus. We are trying to solve for Vc at 0 minus and IR 0 minus. So any thoughts on how we might determine either of those two quantities?
To find IR, couldn't we just like add the resistors together, because aren't they all in series because that open circuit makes it to where that 6 volt doesn't really matter.
Exactly right. Okay. So the suggestion here is that we would take 4 volts and divide it by 2 plus 1 plus 4, looks like 7 kiloohms, which will give us 4/7 of a milliamp. That's absolutely correct. So what is our capacitor voltage going to be?
Would it be 0 because no current can pass through?
So the capacitor voltage can be non-zero even if the current flowing through it is 0. Right? It's an open circuit, so that means that no current will flow through it, but whatever voltage needs to appear across the terminals will.
Do voltage division.
Okay, voltage division would work. So what are we going to put into our voltage division equation?
4 volts times 4 kiloohms divided by the equivalent resistance of 2, 1, and 4.
All right, so I'm going to put that equivalent resistance of 2, 1, and 4 down here at the bottom. So that's going to be 7 kiloohms again. But I disagree ever so slightly about it just being the 4 kiloohm resistor.
The 1 kiloohm and 4 kiloohm are in parallel, sorry.
In series.
Series, not parallel.
Right, so it'll be 5 kiloohms over 7. So this will be 20 of a volt. And we would have gotten that exact same answer if we had simply multiplied the IR at 0 minus that we found by the 1 kiloohm in series with the 4 kiloohm. So effectively what we're doing here, just to be explicit, is we're writing a Kirchhoff's voltage law equation around this loop. And we could easily see then that VC is just IR at 0 minus times 1 kiloohm plus IR at 0 minus times 4 kiloohms. And doing the voltage division method is effectively a shorthand notation for doing that and then Ohm's law in one step or something like that. So any other questions regarding our analysis at t is equal to 0 minus? All right. Now we will analyze the circuit at t is equal to 0 plus. So our 4 volt source continues to be a 4 volt source. Our 2 kiloohm resistor is a 2 kiloohm resistor. We'll talk about what's going on with the capacitor in a second. Here we have our 1 kiloohm resistor. Here is our 4 kiloohm resistor. At t is equal to 0, our switch, so we'll have a short circuit here that will connect the 6 volt source into the circuit. So what should I do with my capacitor?
You can turn it into a voltage source.
Okay. So my voltage source will have the same polarity as VC at 0 minus, and it will also have the same value as VC at 0 minus. So I replace my capacitor with a DC voltage source, positive polarity on top with a value of 20/7 of a volt. And I know that VC at 0 plus, come on, pen thing, has to equal VC at 0 minus. So this is going to be 20/7 of a volt for sure. IR at 0 plus is the current flowing through a 1 kiloohm resistor. So how am I going to find that?
KVL. By KVL in that middle loop. Middle.
Okay,
I mean, can you do nodal analysis? Because I mean, you can say that bottom node's your ground, and then you would have uh you have 3 voltage sources, so that would give you like 3 supernodes.
so the answer to both of those questions is those are absolutely perfectly reasonable ways to do it, but you're kind of overlooking something a little bit obvious. So let's take that nodal analysis idea real quick. But we're not even going to actually do nodal analysis, all right? The voltage present at this node is what?
20/7 volts.
The voltage present at this node is what?
6 volts.
The resistor value is 1 kilo ohm. And so that gives us our resistor current because we know the voltage drop over the resistor and we know the resistor value itself. If we were to do Kirchhoff's voltage law, we would get this exact same thing, right? So let me explain what I mean by that. If we go around this loop, we would wind up getting -27ths of a volt plus 1 kilo ohm times IR at 0 plus 6 volts is equal to 0, which rearranged is exactly that equation. So if we do nodal analysis, we get that result. If we do KVL, we get that result. Or if we use Ohm's law, we get that exact same result. It does not matter which of those 3 ways we can approach this problem. We will literally wind up with the exact same equation. So with that in mind, I'm going to throw this guy into my calculator here because I cannot do that math off the top of my head. So 20/7 minus 6 divided by 1,000 looks like -3.143 milliamps. Any questions regarding the analysis that we've done here at t is equal to 0 plus? All right. So let's move along to t is equal to infinity. At t is equal to infinity, our switch is still closed, but our capacitor will behave as if it were at DC steady state. So we have a 2 kilo ohm resistor here. We're going to have some capacitor voltage VC at infinity. We have a 1 kilo ohm resistor here, 4 kilo ohm resistor here, and then our 6 volt source here. And connect all these guys like so. Here is our current IR at infinity. We need to find VC at infinity and IR at infinity. Any thoughts on how we might determine either of these quantities?
Can we combine the 2 voltage sources into one?
I would argue that they are not in series, so we cannot.
Could you could you do source transformation and get them in series? Or hold on. Maybe.
Possibly. But if we do source transformation, that is going to involve changing the relative position of that 1 kilo ohm resistor, which means that we're no longer guaranteed to be able to find the current flowing through that resistor, because once it changes positions, those quantities are effectively meaningless. It'll absorb the exact same amount of power, but the voltage and current relationships will no longer be valid. All right, so off the top of my head, I can think of a couple of different ways that we can approach this. So I will explain the different ways that are popping up into my head, and you can use whichever one makes the most sense to you. So to me, the most direct means would be recognizing we know that no current is going to branch off and flow down through our capacitor. So whatever current we have flowing through this 2 kilo ohm resistor is the current also flowing through the 1 kilo ohm resistor, which happens to be IR at infinity. So I could say that IR at infinity is 4 volts minus 6 volts divided by 2 kilo ohms plus 1 kilo ohms would give me negative 2/3 of a milliamp, if I did my math correctly. Does that analysis make any sense to you guys?
Yes.
All right. I could, in turn, say that this current flowing through my 4 kilo ohm resistor is just going to be 6 volts divided by 4 kilo ohms is going to look like 1.5 milliamps. Does that make sense?
Yeah.
So I can then see, actually, I don't even need to recognize that. I take that back. I mean, there's nothing wrong with that, but I could say that 4 volts minus 2 kilo ohms times IR at infinity will be equal to VC at infinity. So what I'm doing there is just Kirchhoff's voltage law around this little loop. And I could solve that for VC at infinity. And that would be 4 minus 2000 times negative 2/3 times 10 to the minus 3 is 5.333, which is 16/3 of a volt. That's one way to do it. Let's take this guy again. And look at it slightly differently. Let's erase some of this jibber jabber here. Another way, I'm genuinely surprised that you guys didn't consider. This is mesh 1. This is mesh 2.
Would it have worked the same if we'd have done mesh analysis, or not mesh, nodal, where we could say the VA was on the far left and that would just be equal to 4 volts. VB on the far right would be equal to that 6 volts right there, and then just work it like that, where you'd only have that one node in the middle.
So let's do that down here in a second.
Okay.
We'll beat it to death in 3 different ways to prove that whatever way you're comfortable with will get you the right answer. So using mesh analysis, there are no current sources or anything that I have to worry about here. So for my mesh equation for, for my KVL equation for mesh 1, I'm going to have negative 4 volts plus 2 kilo ohms I1 plus 1 kilo ohm I1 plus 4 kilo ohms I1 minus I2 is equal to 0. And for my second mesh equation, I'm going to have 4 kilo ohms I2 minus I1 plus 6 volts is equal to 0. Solve these two guys, so that'll give us I1 and I2. And we should be able to see that I1 is the exact same thing as IR at infinity. So let's solve that simple system. So my coefficient for I1 is going to be 2,000 plus 1,000 plus 4,000, so 7,000 I1 minus 4,000 I2 will be equal to 4 volts. And then I have minus 4,000 I1 plus 4,000 I2 is equal to negative 6 volts. And I solve this system and I get negative 2/3 of a milliamp here. In my calculator, it's showing up as negative 0.000666667, blah, blah, blah. So that's negative 2/3 of a milliamp. And then I have I2 is negative 2.1667 milliamps, which would be, so that's 1/6, so that's negative 13/6 of a milliamp, if I'm not mistaken. So our IR at infinity matched up, and then we would simply say, well, we'd simply write that exact same Kirchhoff voltage law loop that we got previously. So 4 volts minus 2 kilo ohms times I1 is equal to VC at infinity, which would give us VC at infinity should obviously be, what did I get? Well, let me set it up here. 4 minus 2,000 times the variable I have stored as X. 5.333, which is 16/3 of a volt. So we get the exact same result using mesh analysis. So someone else suggested potentially doing nodal analysis. Let's do that too. So let's put our ground here. This will be VA, VB, and VC. VA is 4 volts. VC is 6 volts. So we can say that VB minus VA over 2 kilo ohms plus VB minus VC over 1 kilo ohms is equal to 0. That's the currents flowing to the left from node B and the current flowing to the right from node B. Solving these guys, we'll get VA is 4 volts, VB to be determined, VC will be 6 volts. So let's throw this system into our calculator. So if my first equation is VA is equal to 4 volts, so I have 1 VA plus 0 VB plus 0 VC is equal to 4. My second equation is VC is equal to 6 volts, so I have 0 VA plus 0 VB plus 1 VC is equal to 6. And then my third equation, I have negative 1 over 2000 is my coefficient for VA. My coefficient for VB is 1 over 2000 plus 1 over 1000. And my coefficient for VC is negative 1 over 1000. And my constant term is 0. Solve. I get 4, 16/3, and 6, where VB is easily VC at infinity by inspection. And then I could say that IR at infinity is simply VB minus VC over 1 kilo ohm. Or negative 2/3. Gosh, that 2 looks like garbage. Negative 2/3 of a milli. So legitimately, any way that you can solve it will get you the correct answer. So we've solved it using effectively Ohm's law and KVL, using mesh analysis and using nodal analysis. It does not matter which way we go about it. We will get the right answer if we apply our circuit analysis technique correctly. So circling back around to the problem at hand, step 4 is going to be calculate tau and plug stuff in. So let me get my circuit here. Oh, you're not going to be difficult with me, are you? All right. So let's erase some of this jibber jabber that we don't need. So during the transient condition, if we're trying to find the equivalent resistance, we take our capacitor out and look into the dead network. So that's where our capacitor was. So that's where we're going to be looking in. Dead network means we have to turn off our voltage sources. So what is our equivalent resistance?
Three kilo ohms in parallel with 4 kilo ohms.
I disagree.
There's no current. They're all in series.
Also disagree.
Would it just be the 3 kilo ohms because technically that 4 kilo ohm is shorted out?
Okay, so the 4 kilo ohms is shorted out. I agree with that 100%. So the 4 kilo ohm resistor does not contribute. So we can erase that. But it is not 3 kilo ohms.
2 kilo ohms.
Not 2. All right, so you guys are blindly guessing. Let's identify our nodes and figure this out. There's one node. There's another node. So it should be pretty obvious now that the 2 kilo ohm resistor appears in parallel with the 1 kilo ohm resistor. So it'll be 2K times 1K over 2K plus 1K is 2/3 of a kilo ohm. Does that make sense?
Yes. I wasn't paying attention to the how it split off right there.
Yeah, no problem. Anytime you are trying to find the equivalent resistance of pretty much anything, I would go through the trouble of identifying my nodes and all that kind of stuff just to be on the safe side. Like, even if it seems pretty obvious, I would still do this just to make sure. All right, so that's our equivalent resistance. Our equivalent capacitance was 150 microfarads. So our time constant here is just going to be RTH times C. So that is 2/3 times 10 to the positive 3 multiplied by 150 times 10 to the minus 6. Looks like 0.1 seconds. So tau to the minus 1 power is then going to be 10 per second. And so finally, then we'll have VC of T. So what was VC at 0 minus? It's been forever ago, so I don't remember.
20/7.
20/7 volts for T less than 0 minus. Okay. So then we're going to have 20/7 minus VC at infinity, which was 16/3, right?
Yes, sir.
So 27th minus 16/3 looks like negative 52/21 e to the minus 10t 16/3 volts for t greater than 0. Just to be clear, this number comes from taking VC at 0 plus minus VC at infinity. Our resistor current, IR, as a function of time. So what was IR at 0 minus?
4/7 milliamps.
All right. And then we have IR at 0 plus, which is not going to be 4/7 of a milliamp, or it doesn't have to be. Let's see what we got up here. That's still looking at stuff at infinity.
It should be -3.143.
All right, negative 3.143. Thank you. So negative 3.143 minus IR at infinity, which we got to be negative 2/3 of a milliamp. So this looks like negative 2.476 e to the minus 10t minus 2/3 milliamp for t greater than 0 plus. So let me make sure I got that sign correct. So this was negative. Okay. It was, just to be clear, this comes from 3.143 milliamps minus negative 2/3 of a milliamp, which was IR at 0 plus minus IR at infinity. So that was a transient analysis problem. Any questions, comments, or concerns? All right, what would you care to talk about next? All right, so it sounds like we're wrapping things up here. I'm gonna have this video and yesterday's class meeting video uploaded this afternoon. It was brought to my attention that my old practice tests that I have given you guys do not currently include any op-amp circuits. So I will be pulling the op-amp circuits from old exam 3s and compiling them into a kind of just like a little practice session on op-amp analysis. I will also be doing that this afternoon and have it uploaded for you as well. I should be around on my computer most of the day tomorrow. So if you have any questions that pop up as you're trying to study, by all means, shoot me an email and we can either resolve your question by email or I may be able to get on Zoom and all that kind of good stuff as well. Good luck with all your studying and all that kind of stuff. Again, if you have any questions, by all means, just feel free to ask and I'll talk to you guys on Monday if I don't have to talk to you before then.